This session will start momentarily. Please note, this session is made possible by the generous support of Concord Engineering, a leader in the microgrid industry. While at the conference, please make time to visit their booth to learn more about Concord Engineering's microgrid solutions or to schedule time to speak with a representative. Hello, my name is Kevin Normando, and welcome to the Microgrid Knowledge virtual tour of the Princeton Medical Center microgrid. Normally at our conferences, we will have several busloads of folks go over to a local microgrid so they have an opportunity to tour the physical plant. However, this year with the global pandemic, we're going to do this tour virtually. This will allow you a unique opportunity to get inside of the plant, as well as the opportunity to speak to several of the experts. Today's speakers include Joe Sullivan, Vice President of Energy Policy and Development at Concord Engineering, Robert Tweed, Development Engineering Manager at Clearway Energy. We also have Mike Webster, CTO, IceTech Energy Services. After the tour, you will have an opportunity to ask questions of these experts. So you'll notice on your console, there is a tab that says poll. If you go into poll, you can enter in a question, or if somebody has already submitted that question, you can vote it up and we will do our best to answer those questions after the tour. Thank you very much. And now let me turn it over to Joe Sullivan.
My name is Joe Sullivan. We're talking about the Energy Center and the Cogen project at the Medical Center in Princeton, which is currently operating and has been for quite a number of years now. At the time this project initiated, I was actually the energy ombudsman for the State Board of Public Utilities. And to talk to them about how can we do better energy efficiency? Can we do cogen? Can we do renewables? Can we integrate and create a better project from the start? Because we've always known that adapting systems after the fact is definitely not optimal. And you may wind up spending money that you don't need to, or you wind up with systems that don't work as efficiently as they could. So what happened was I went up and met with the principals of the hospital, and this is a brand new state-of-the-art facility. And they were challenged by a lot of things. They wanted to be an efficient operation. They wanted to be energy efficient because they felt that there was an obligation in terms of environmental issues and energy issues. But they also had budget issues and cost issues. So we introduced the concept of cogeneration to them. And of all the things that we could offer them from the state side, that got the largest number in terms of dollars of support. And we discussed with them the possibility of bringing in third parties who could do that on their behalf. We subsequently agreed to work with the hospital from the state and help them go through an RFP process to select a developer who could bring a third party in, which would put up the financing and the money for the cogen project and do it as a full third party deal. Clearway Energy was the firm that was selected and developed this not just as a cogen project, but to do a full integrated central utility plant. The firm I currently work for, Concord Engineers, as a design engineer and actually eventually as the construction manager for the project. And it was changed from simply being a CHP plant to being a full central utility plant. And it included, and it was wise to do so, the emergency generators, the chillers, the absorption chillers, the thermal storage tank, the boilers, as well as the cogen project. It has been a great experience to work through this with Rob and with Mike Webster and all the other people who are involved in this, because we typically get involved in the engineering. We don't have to live with it. And these guys lived with it and optimized it. And they took, I think, a good, capable plant and made it operate in ways that we didn't really anticipate. And it made it a better plant. And I think by staying in touch with them and working with them, it makes us better engineers. So Rob's been a great guy to work with, and I'd like to turn this over to him to take this through the next phase of describing the central utility plant and cogeneration.
Hello, everybody. My name is Rob Tweed. I am presently Development Engineering Manager with Clearway Energy, and we are now the owners and operators of the Princeton Energy Center. We have here Princeton Medical Center, Acute Care Hospital. The utility plant, or the central utility plant, is located on the northeast side of the campus. It's a very unassuming facility. On the northeast side of the campus is a solar array and a 200 kilowatt integrated solar array that goes into one of the hospital main substations on the building 2 side. The microgrid, and we'll show you here the one line diagram here for a second. What we have is a main 13 kV bus. Feeding in on the A bus is a 4.6 megawatt gas turbine generator. And feeding in on the B bus is the 200 kilowatt solar array. And then we are also tied to through a transformer to a 4160 volt diesel generator emergency substation. That bus itself is always energized, which gives us a lot of flexibility. We'll switch over here to the electrical HMI. And we have the entire facility is controlled from, a central control room. And we have, full status of the entire electric system from one central spot. And then we can drill into the CAD ISO control system, which manages the diesel generators themselves and allows us to conduct testing. And we test right on the grid. We don't need a load bank. Because the system's always energized, we simply synchronize the diesel generator to the bus. It automatically backs down the gas turbine. We do something useful with the electricity while we're testing our half an hour every month on each engine. And while we coordinate, activities in the plant. The upper level, as you walk into the plant, you'll enter the main substation. We have a dual feeder configuration. We're connected to two PSE&G, the electric utility, by two 13 kV full load capable feeders. So we can run on one alone. And that's how we normally operate. One feeder closed, the bus tie closed, and one feeder open on hot standby. And we manage those two feeders using an SEL 351 feeder management system where that allows us to spread the gas turbine energy across the whole hospital campus. And God forbid there's an interruption on one of the feeders, it will automatically swap to the secondary feeder, within milliseconds. And that's our first line of defense before, the 10-second timer would bring in and synchronize the emergency diesels. Moving into the emergency substation, again, we have a dedicated emergency substation. We have, 3 2 megawatt emergency diesel generators. Their main breakers are right here on that bus. And again, managed by the CAD ISO control system, which through Modbus is monitored by the main plant control system. And we can dispatch and control the operation of the diesel plant from the control room. We'll walk into the emergency diesel generator room itself, where we have these 3 CAT 3516 diesel engines, each good for a full 2 megawatts of power. The hospital load is only about 2 megawatts, so we're actually in +2 right now, but we're ready for a little bit of future growth if the hospital decides to add any additional floors or any additional buildings to their campus. We could handle that without any big changes. Take you into the cogen room. This is where our gas turbine and heat recovery steam generator are located. We have a Merc 50 gas turbine generator, and we'll show you the gas turbine. And off to the left in that picture is actually a dispatchable air inlet cooler. And that's where that air inlet cooler is one of the many tools that we have to utilize the thermal energy that we store in our thermal energy storage tank and to improve the overall Brayton cycle efficiency of the gas turbine. We may or may not run the air inlet cooler depending on what our market conditions, our electrical market conditions are. And we use the IceTech control system and energy management system, or another way of looking at it is plant to market optimization system, to give us the intel that we need on when to dispatch that air inlet cooler and use it effectively. because there is a limited amount of thermal energy that we have in storage, and we want to get the most out of it by doing things at the right time. We'll take a quick peek inside the gas turbine because it is a very interesting engine. The Merc 50 is an ultra low emissions engine. We're doing 4.6 megawatts at a very predictable and consistent 4 ppm NOx, okay, and with a barely discernible CO. And this is just a remarkable engine. It has a recuperator on it, which takes the exhaust energy and passes it to the compressed air after it leaves the compressor on the turbine and before it's sent into the power turbine and combusted. So it does that extremely well, and again, very consistently. Quick shot here of the compressor, the Merc 50 compressor. This is where it takes in the air and compresses it to the required pressure before we send it to the burners. And then we have a Merc 50 generator, the generator set, which is actually a Cato generator, probably roughly a 5,000 kVA unit that's attached to the York epicyclic gear. We altogether ties into a really awesome little package that served us extremely well, with our uptimes being in the high 90s. Take a quick shot of the Herzig heat recovery steam generator HMI here, and you'll see that even though it is a once-through type boiler, it is a water tube boiler. It's a water tube boiler with a generator bank in the back and a very large economizer, which improves its overall efficiency. A shot here of the duct burner, which is the bread and butter of this whole setup. The duct burner brings in an interesting and situation where every BTU that we bring in gas is actually converted to steam. Okay, a super high efficiency once we bring that duct burner on. And so regardless of the output of the turbine, we're able to bring that duct burner in and make very efficient steam. Okay, and that's really good for the customer, regardless of the market conditions. Sometimes the electric market is extremely competitive, and sometimes it's very soft. But regardless, we're still getting value by using this duct burner to take care of the steam needs of the facility. We'll take you quickly outside to the cooling towers. We have ultra quiet fans on this cooling tower array that takes care of our chillers downstairs. Of course, we're extremely sensitive to Legionella, and so we do Legionella testing every 2 weeks. We report to the EOC committee in the hospital. And again, just as if we were a department, we send those results. We have a extremely tight Legionella protocol. We disinfect with hydrogen peroxide, in addition to running a oxidizing and non-oxidizing biocide scheme to keep the tower nice and clean. Typically looks like a swimming pool when we're running it. And we have one of the interesting things about having a thermal energy storage tank, and we'll show you that in a second, is that you're able to shut down and keep that tower super clean. We'll actually get in there with a pond vac, and suck out the dirt. And it's been our experience that a really clean cooling tower, when there's no mud or dirt inside, it's almost impossible to get Legionella in that tower when there's no mud in there. Take a quick peek at the gas compressor. The gas compressor is necessary because the street pressure of the gas only takes us to about 50 psi, and we need about 150 psi at the injector. So we need this gas compressor to bring up the gas pressure and to normally run the turbine. It does have a variable speed drive on it, so it does match its energy use quite well, and becomes part of our cogen train. We'll take a quick peek over here at the thermal energy storage tank. I mentioned that before. This is actually a 1 million gallon storage tank and works out to be about a 10 megawatt hour storage battery. That's the way I see it as the plant. When we look at it, it is each chiller train that we have, that's the chiller, the pumps, the fans, roughly equates to about a megawatt of energy being used. And the thermal energy storage tank, when it's dispatched, takes 1 megawatt off our load. Okay, so when the market conditions are at a point where it's time to dispatch, this tank is like just putting on a battery. It allows us to shut down the chiller and provide that chilled water to the hospital, and it's totally seamless to them. They have no idea that we're in a dispatch mode. The tank itself is a really simple design. It has spiders on the top and on the bottom of the tank. It works on a thermocline principle, where at the top, the water temperature could be 58, 59 degrees Fahrenheit. And at the bottom, it could be 39, 40 degrees Fahrenheit. And there's about a 1 foot band of 2 temperature waters at different densities. And of course, the colder water, being more dense, sinks to the bottom. And we lay it into the tank very gently using those spiders, and that prevents the tank from getting mixed. And so the whole tank works on a thermocline density principle, and it works extremely well. And it's just chilled water. It's just water with a little bit of corrosion inhibitor and biocide in it to keep the system clean. Take a quick peek over at our fuel tank farm. We have 2 40,000 gallon storage tanks. We use ultra low sulfur diesel fuel. Everybody in New Jersey does. And that will take care of our diesel generators and our package boilers as well, which are dual fuel. And we have about enough fuel on hand to run the hospital for 2 weeks at full emergency power load, or 1 week if we have to run the package boilers as well. All right, we'll go downstairs into the boiler room. We'll take a quick peek at the steam HMI, and you'll see that we have 3 package boilers. They're Cleaver Brooks 700 horsepower, dual fuel, low NOx. They do like a 15 ppm NOx on natural gas and about 38 on oil. And although natural gas is our by and far primary fuel, we are actually a firm gas facility right now, from both a risk and it's almost a hedging strategy to an extent in terms of the firm gas. And we're gonna talk to Mike Webster at the end of this presentation, and he's going to give us a little insight into fuel purchasing. We'll take a peek here at the package boiler setup. You'll see the 3 boilers there. Again, they're very. It's a nice little package. The Cleaver Brooks. It's a 700 horsepower. Roughly, each boiler does about 20,000 pounds an hour of steam at about an 85% fire. We typically will, again, primary fuel, natural gas, but secondary fuel is fuel oil. And we do test monthly to make sure that the operators are always able to run on oil. We don't want to have a fire drill. God forbid there was a gas interruption. And it has happened, although it is very rare to lose your natural gas. We're prepared for it if it does happen, and we can take care of the hospital and their critical mission. Take a quick peek here at the deaerator. It's a 5 PSI, typically deaerating feed water heater, and a surge tank over there to the right, which where all the hospital returning condensate comes back. During the normal part of the year, we're better than 90% condensate return typically. In the winter, the hospital does do direct steam injection for humidification. So we do tend to get, we can lose up to 15,000 pounds an hour of steam to humidification in the winter and the really dry days. So we do have to bring in a little bit of makeup water, for that purpose. We have just a sodium zeolite water softener. We'll just show you a shot here. It's a three unit water softener to handle. We added another unit because of the steam humidification requirement that became a consequence out of construction. A little air compressor skid here to handle some of our larger compressed air operated valves. And we have a remote HMI, which brings in a lot of our analog and digital IO from the chilled water plant, and also serves as a control point so that the operator doesn't have to run upstairs to the control room to do something. He can do it right from that HMI and run the whole plant from that little screen if he needs to. walk you into the chiller room where we have three electric 1,000-ton chillers and one 700-ton absorber. Take a quick peek here at the chilled water HMI. And we'll look over here at chiller 1 and 2. And then take a quick peek over here at the absorber in chiller 3. And look at the 700-ton absorber again. The three electric chillers are, again, 1,000-ton machines. And the way we'll typically run the chilled water plant in the summer is the absorber will primarily serve a primary loop, or the primary loop in the hospital. And the primary loop is taking the return water from the hospital and sending it to the chillers or the TES tank. Again, sending it to the chillers or TES tank. And what we're doing is we're recirculating that primary loop water through the absorber, which acts for the most part as a dump condenser for the surplus steam that we get from the HRSG when it's at full power. The secondary pumps the secondary loop will take the water from the chillers or the TES tank and then send it back to the hospital to the various air handlers that are there in the plant. And what's really cool about it is the TES tank can serve the hospital exclusively, and you don't have to. We may run just we can reconfigure the absorber to either be a direct provider of chilled water to the hospital and mix that the output water from the absorber and blend that in with the primary flow coming from the TES tank. So that even though the output from the absorber might only be 45 degrees, the TES water's at 39 and an overwhelming flow. So it will still provide, you're still getting useful energy and, from this really, sort of cumbersome machine that, most people look at as kind of a pig. It actually becomes quite of a critical part of our dispatch strategy on the really hot days, and again, very, very versatile in terms of how we have it configured. Final shot here of the condenser water pumps. These just take care of the chillers and the cooling towers. And all the big pumps in the plant are on variable speed drives, and that was part of the original Concorde design to get the most energy efficient configuration of the plant equipment. We're going to end up here in the control room. And it's a, ControlLogix, Rockwell ControlLogix platform with a factory view HMI, very operator friendly graphics, easy to use. And again, the primary screens that the operator are seeing are the chilled water HMI. And in there, within chilled water, we have Rockwell wire to water optimization, where we're coming up with the right combination of pumps at the most energy efficient dispatch speed, working to either a single or double loop, double PID loop, depending on the pressure and flow. You see the steam HMI here, and again, this is just a quick view. We've seen this before, but and again, you've got the three package boilers and the cogen boiler and the HRSG and all the critical parts. Here, a lot of this is being communicated again just through a Modbus interface into the main plant PLC and being rebroadcasted here on the screen. And we have some of it dispatchable, some of it being view only. We have the cogen HMI here. This is the solar HMI and plant trending. We use the trending quite a bit actually to identify and troubleshoot issues that are occurring in the plant. We also have a hospital interface screen where we can see all the hospital's air handlers and pressure reducing valves. The steam system serves 4 primary PRV points in the hospital, and we send pressure at 150 PSI, and it's reduced down to 15 PSI for the most part inside the building. We also have the hospital automatic transfer switch system. They have a gaggle of automatic transfer switches. We can see the status of those systems in an emergency. We can see the status, and after an emergency, we can make sure that all the ATSs have recovered to their normal positions as our diesel generator looks to come back to standby position. And finally, the one piece of equipment, the one control piece of equipment that kind of puts it all together for us is the Ice Tech control system. And this is the Ice Tech main HMI. And you got a big weather screen here on the bottom, and then you can see the dispatch bar across the top, sort of showing us the the status of plant equipment. It's a soft time of year right now, so not a lot of excitement. But during the summer, our eyes are constantly on these screens. And one of my sort of favorite screens, because this is one of our primary focuses during the summer, and certainly the area where us as operators can provide maximum value, is the Ice Tech Scorekeeper screen, where to the left you'll see our PJM capacity charges, both the generation and the transmission charges. And you'll see those number, and I don't know if there's enough granularity in the picture, but you'll see that we had a banner year this year, and that our demand scores are going to be remarkable. With a facility that has a 6.5 megawatt total presence to grid potentially, that we during the times that that were important, and I'll let Mike elaborate on this a little bit more, but during those important times, we were hardly on the grid at all, for 20 or 30 kilowatts. Okay, and that let's take me to one more shot here of the monthly demand charges, and this is probably the most important thing that we do. One of the most important things that we do is that when you look at these monthly charges, one, you'll see that this is actually based on last year's presence to grid. Okay, so you'll see here, scores in the hundreds of kilowatts, a couple of 100, 150 kilowatts, and for both the generation and the transmission. And each one of those has a monthly value of, either $12 and change, or $11 and change, depending on which one it is. But the aggregate effect of these two charges together is $295 a kilowatt year. That's 1 kilowatt for 1 year. Okay, that's what you're spending for demand. So when you have a 6.5 megawatt potential presence to grid on a really hot day, on the worst day of the year, during a heat wave, okay, and that's how your actual demand charges are calculated. We're talking about a plant system that can't produce that much energy on a steady basis, but because of the timing and the dispatch strategy and the plant to market optimization tools that we have, we're avoiding over $1.5 million, okay, in cost, okay, which is just remarkable. And that's a really good segue to introduce Mike Webster. He's the Chief Technical Officer and founder of Ice Tech Energy Systems. Mike, take it away.
It was very interesting listening to you. You're right. Princeton Hospital is a really good example of a microgrid. You have all the toys in the toy box. But the thing that's impressive about Princeton Hospital is how well they work together. There's a lot of folks out there that try to build these things or add on to them, and they have solar and TES or battery storage and cogeneration, and they don't really work that well together. But yours is very fluid, which is also a testament to Mr. Sullivan as well and his crew. It was really well designed, and when that happens, it just works. So Ice Tech comes along and has this really dynamic plant, and what do we do with it? Well, first thing we want to be is efficient. So we look at the efficiencies of the duct burners you spoke about, look at the efficiencies of the absorber, the heat recovery, the electric chillers, and the first order of business is to create a dispatch system that is as effective as it can be and be economic at the same time. And so we do have a lot of market data. We have a lot of market analytics to help us do that. And the object is to be in the best place economically in the market, also efficiency, and therefore carbon. And that took some time to do, but we've brought this technology that we use And it was really a lot easier to achieve at Princeton Hospital because the system works very well. 90% condensate return. I mean, the turbine inlet cooling effectiveness, all that stuff is just really good. It does make our job a little bit easier. The next layer up from that we worry about is your fixed charges of capacity and transmission. So because it's so dynamic, we can really zero in on the hours that we need to worry about. We need to worry about the 5 highest PJM hours, obviously, but in PSEG, we also need to worry about the 5 highest PSEG hours. And to be able to react quickly to that and aggressively to that, and to do things like reserve the TES tank for maximum capacity that you wouldn't do every day. You wouldn't pump the way that you do on those events that you would do every day. And doing that and dispatching you guys has really been tremendous. The next layer up from that we look at is, it really does, the plant overall matches the load of the hospital pretty well. But you do have some excess capacity. You do have some excess, not only from an electrical generation point of view, but from a heat recovery point of view as well. So over the last few years, we worked with all these guys, and we became a market participant, not in demand response, but in ahead of the meter in generation. So we are an energy only wholesale market participant in the PJM market. Some months that's a couple hundred hours, but you get into a winter vortex situation, it could be several tens of thousands of dollars because of the volatility in the marketplace. And on the next layer up from that is really managing your hour-to-hour spend, and that includes looking at the best way to contract for power and also the natural gas. And we are on a real-time power rate from PSEG, which is very advantageous to you. And that works out well because we can predict that volatility. We can shift the turbine, we can shift the TES in anticipation of the predicted higher cost hours. So it's kind of like this, it's all one pie. When I think about the management of the gas contract and the electricity contract, it's because we have this pie, and it just kind of adds to the pie. It's all one thing at the end of the day. It's effectiveness and efficiency. So that's about all I have to say. We can go into how we do it. We have a bunch of analytics. We have a data center in Philadelphia that looks at all this stuff and decides what to do. But overall, it's a really effective plant, and we're happy to be part of it. So with that, I'll send it back to you, Rob.
So, I kind of like, the Princeton Energy Center really is sort of like that energy Swiss Army knife. When we first built the plant, gas was practically $10 a decatherm to city gate, and now it's $2, and so, but regardless of, how it was designed, and this really goes back to the versatility of the design that Concord designed and built for us, is that it still all works, that, and that's where the plant to market optimization that Ice Tech provides just brought in that additional value, a robust and versatile platform that Concord brought us, really allowed us to do these things. And then just the culture that we have operationally within Clearway and our team, that even our operators are contributing to the bottom line by creatively dispatching and even managing the variable speed fans on our cooling towers. So thank you so much, everyone, for joining us, and have a great day.
Thank you very much, Rob. And thank you to Joe and Mike for your time and insights. And now is the time to turn it over to our audience, and we'll try to answer as many questions as we can. If you have not done so already, please navigate over to the polls tab on your screen and either type in your questions or vote up the questions that you would like to hear from these experts.